Hello everyone, I'm Grzegorz Dudek from Częstochowa University of Technology, Poland. I will present my research results on autoencoder-based randomized learning of feedforward neural networks. First, short introduction, then I'll characterize randomized learning of feedforward neural networks. Then I talk about generating hidden node parameters using autoencoders. I'll propose some modifications of the standard approach. I present some experimental results on comparing autoencoder approach with other methods proposed recently. And finally, I conclude the work. Feedforward neural networks have excellent predictive performance and universal approximation capabilities. The most popular learning methods involve some kind of a gradient descent algorithm, which suffers from many drawbacks, making the learning process ineffective and time-consuming. As an alternative to the conventional feedforward neural networks iterative learning using gradients, randomized learning was proposed, where the parameters of the hidden nodes are selected randomly and stay fixed. This makes the optimization problem convex. Randomized learning is very fast. Network has good generalization properties and is easy to implement. A challenging and still open problem in randomized learning is how to choose appropriate weights and biases for hidden nodes to ensure the best model performance. Recently, unsupervised parameter learning using autoencoders was proposed, which brought very good results in classification problems. In this study, we analyze this method for regression. We compare this approach with alternative methods which were proposed recently. In this study, we consider a single hidden layer feedforward neural network with single output with weights A and biases B generated randomly or using autoencoders, with M hidden nodes, activation functions H, we use sigmoids, and output weights beta. The network expresses function phi. The output weights beta are determined using the Moore-Penrose generalized inverse of matrix H. H is a hidden layers output matrix. Typically, weights and biases are selected from fixed interval -1, 1. The middle panel of this figure shows the sigmoids which parameters were selected randomly from this interval. Note two drawbacks. Sigmoids are too flat, and many of them have the most steepest fragments, which are around the inflection points outside the input interval, shown as a gray field. These steep fragments are most useful for modeling the target function fluctuations. The sigmoids are combined linearly. The lower panel shows sigmoids multiplied by the output weights beta. The sum of these functions gives the fitted curve, red line in the upper panel. For the standard interval for random parameters -1, 1, we get very poor fitting. Result doesn't improve when we increase the number of nodes to several hundreds or even thousands. Fitting improves when we optimize the interval for the random parameters. For the interval -10, 10, the sigmoids are steeper and are able to fit the target function. But note that still many sigmoids have the steepest fragments outside the input interval, having the saturated parts in it. They don't build the fitted curve and are useless, so can be removed. Recently, several methods for generating random parameters were proposed. One of them, RAM, selects weights A from interval -u, adjusted to the target function complexity. Then the biases are determined in such a way as to ensure the steepest fragments of the sigmoids into the input hypercube. The resulting biases are dependent on the weights and some point x asterisk from the input hypercube. In this study, this point is selected randomly from the training set. This approach gives the perfect fitting and no sigmoid is wasted. An alternative method, R alpha M, generates sigmoids with uniformly distributed slope angles. This method first selects randomly sigmoid slope angles from the interval adjusted to the target function complexity, and then calculates the weights. Biases are determined in the same way as in the case of RAM to introduce the sigmoids into the input hypercube. And now let's focus on the unsupervised parameter learning using autoencoders. This is a randomized autoencoder with hidden node parameters, weights W and biases C selected randomly. The encoder maps the input data randomly into some latent representation such that the decoder is able to reconstruct the original input data from this representation. Randomized autoencoder has M hidden nodes and sigmoid activation functions, G. The output weights are determined easily using the Moore-Penrose generalized inverse of matrix G. These output weights are considered as the latent features of the input data and are used as the hidden node weights for the predictive model instead of random weights. As for the biases of hidden nodes B, it is hard to find in the literature how they are selected in this unsupervised approach. The exception is this work, where the authors suggest to calculate the bias for the node as the mean value of this node weights. Let's look at this case from the perspective of activation function distribution in the input space. When the bias is defined as the weight average, the inflection point of the sigmoid for the one-dimensional case, which is for h equals to 0.5, can be obtained from this equation. Thus, the inflection points of all sigmoids are in x equal to -1. We substituted a for b here. This case is shown in the figure. Note that the steepest fragments of the sigmoids, which are around point x equals to -1, are far from the input interval. This interval includes many saturated fragments of the sigmoids, which results in poor fitting. To improve the model performance, we use the same solution for biases as in RAM and Rα-M. We calculate them from this equation on the basis of weights A produced by autoencoder and randomly selected training points x asterisk. Thus, we distribute the sigmoids in the input hypercube according to the data distribution. The results for the one-dimensional case is shown in the figure. As we can see, the accuracy didn't improve significantly. This means that the problem is not only due to the misdetermination of the biases, but also due to the too flat sigmoids that don't correspond to target function complexity. The sigmoid slopes in the regression model are determined by the randomized autoencoder output weights V. These weights are dependent on the autoencoder hidden node random parameters W and C. In the above described simulations, these parameters were both selected from the standard interval -1, 1. As we shown earlier, this is an incorrect approach. Thus, to improve the regression model performance, we propose to use RAM for generating W and C. According to this method, we optimize the interval for W and calculate the biases C from this equation. These figures show the effect of the interval bounds on the median of absolute values of weights V, left panel, and on the fitting error, right panel, for target function analyzed earlier. Note that the median of V decreases quickly with bounds U. Error reaches its minimum for U from 0.05 to 0.2. For such bounds, a randomized autoencoder produces weights V whose median is in the range from around 5 to 14. For such a case, error reaches an acceptable level, which is similar to those obtained by RAM and Rα-M for the same number of hidden nodes, 25 in this case. These figures depict fitting results for u equal to 0.1. A very good fitting and no wasted hidden nodes. But it should be noted that the optimal interval for weights w depends on the number of hidden nodes. And the results of these findings. And the output weights v produced by randomized autoencoder determine the sigmoid slopes in the regression model and are crucial for accurate target function approximation. These weights are dependent on the randomized autoencoder hidden node parameters, that is, weights w and biases c. The standard weight of generating both these parameters from the same interval is unjustified and misleading. We recommend optimizing this interval for weights w and determining biases from this equation. The optimal interval for weights w depends on the number of hidden nodes m. Thus, for each value of m considered, this interval should be optimized. The hidden node biases of the regression model B determine the sigmoid placement in the input space. They should introduce the steepest fragments of the sigmoids into the input hypercube. Incorrectly selected, they lead to the placement of the saturation parts of the sigmoids into input hypercube. To avoid this, we recommend determining biases from this equation. To demonstrate the fitting properties of randomized autoencoder-based learning, we report some simulation results over several regression problems. They include an approximation of extremely nonlinear target functions, as you can see on this slide. We consider these functions with 2, 5, and 10 arguments. We use our proposed modified version of Autoencoder. For comparison, we use RAM and Rα-M. As can be seen from this table, Rα-M demonstrates the highest fitting accuracy for all target functions. Results for randomized autoencoder and RAM are similar. These figures depict fitting test error depending on the number of hidden nodes. In most cases, Rα-M keeps error decreasing with the number of nodes, while other methods reach a minimum level or even start to increase in some cases. The confidence intervals for RAM and randomized autoencoder overlap in most cases. And this means that these two methods generate similar weights A, which provide a similar set of basis functions for regression model. Although randomized autoencoder, unlike RAM, doesn't generate uniformly distributed weights A. Interestingly, for each target function, Rα-M generated weights A from the same distribution. This table shows results for several real-world regression problems. Again, the best results for Rα-M. The worst results for autoencoder method, in italics. This box plots compare the proposed modified randomized autoencoder with its other variants, in which some random parameters are selected from the fixed interval -1, 1. The proposed modification in most cases gave the lowest errors compared to other variants. Conclusions. We showed that the randomized autoencoder-based randomized learning of regression neural model suffers from several drawbacks. It produces the weights for the regression model by taking into account just the input data, ignoring completely the target function. It doesn't generate the biases for the regression model. We propose improved unsupervised parameter learning using randomized autoencoders. We introduce the possibility of controlling the magnitude of the random weights produced by randomized autoencoder, and we determine the biases for the regression model so that the sigmoids have the steepest fragments introduced into the input hypercube. These modifications make the randomized autoencoder method more flexible and more dependent on data and more dependent on the complexity of the solved problem. Unfortunately, the experimental part of the work doesn't provide evidence that the improved autoencoder approach outperforms in fitting accuracy other new methods of generating random parameters. Moreover, its complexity is much greater as it requires additional learning of randomized autoencoder. Therefore, applying it to regression problems rather than simple and faster methods may be questionable. Thank you very much for your attention.